Hello dear student, welcome to new session of magnetic effect of current. In last class we will discuss magnetic field due to current carrying circular loop, magnetic field due to current carrying circular arc, and we'll solve some numericals. So please write down one more numerical. Write down find the magnetic field find the magnetic field at the center find the magnetic field at the center find the magnetic field at the center O at the center O due to the given part if current in the given system if the current in the given system is 5 ampere if the current in the given system is 5 ampere and the diameter of the coil is 10 centimeter and the diameter of the coil is 10 centimeter. So my dear student, basically in this question they are asking to find the value of magnetic field at point O, and they are defining the diameter of this coil. So diameter of coil is 10 centimeter and we want to find magnetic field at this point O. So see, basically we have here three different structures. Consider the diagram to be three different structures. One is plain wire, another is also a plain wire, and other is loop. So my dear student, if you will see here, then this loop carry two different direction. In this loop the current is in two different direction. One is in this part and second is in this part. So let's suppose the points are C, B, D. Let's suppose E, this is P and this is Q. So if you will see in this loop, the part C, B, D carry in this direction current, and if we'll see this part of this loop, that is C, E and D, the direction of current is like this. So my dear student, both the current carry same magnitude, it is 5 ampere, and both the current are in opposite direction. So we can say this magnetic field due to this part and magnetic field due to this part. Due to both the parts, the magnetic field is same, but the direction of current on both the part is different. So see, we know that the magnetic field due to current carrying loop, the direction of magnetic field due to current carrying loop is given by right hand screw rule, in which we have to curl our right hand finger in the direction of current and thumb can give you direction of magnetic field. So see, due to this part, that is CBD, the direction of current is like this. So I am curling the finger in the direction of current, thumb can give the direction of magnetic field. So due to this part of loop, the direction of magnetic field is away. If we talk about this part, that is C, E and D, the direction of current is like this, so magnetic field is inside. Now see, basically due to this part and due to this part, the magnitude of magnetic field at point O is same, but their direction is different. So due to this loop, the net magnetic field at center, my dear student, will be 0. So I am writing here magnetic field due to loop. I am writing here magnetic field due to the loop, magnetic field due to the loop at point O is 0. I hope you all understand the direction of magnetic field due to this part of current is away and direction of magnetic field due to this part of current is towards. So net magnetic field at center due to this loop is 0. Now moving forward. Now see my dear student, we have this PC is one wire and QD is another wire. If you will see, we want to find magnetic field at this point O, and this point O is present at one end of wire my dear student, and the length of wire is not given. So I am standing in front of one end of wire and other end is tends to infinity. So both the wire is considered to be semi-infinite wire. I hope you all are understanding this thing, because remember semi-infinite wire was like this. I am standing at one end of the wire and other end. So alpha becomes 0 and beta becomes equals to 90, because other end of wire tends to infinity. So my dear student, this wire is nothing but semi-infinite wire, and this wire is also semi-infinite wire, because we want to find magnetic field at one end of wire at point O, which is present at one end of wire, and other end is other end of wire tends to infinity. So magnetic field due to semi-infinite wire, I hope you all remember the formula. Magnetic field due to semi-infinite wire. Semi-infinite wire is mu naught I by 4 pi a sin alpha plus sin beta. Sin alpha is 0, sin beta is 90. So magnetic field becomes equals to mu naught I upon 4 pi a. Now see my dear student, a is basically distance, and this distance must be perpendicular distance. So if diameter is given, then this distance must be 5 centimeter and this distance is also must be 5 centimeter. So from both the ends, from both the wire, the point where we want to find magnetic field is 5 centimeter apart. Now see the direction of magnetic field due to both the wire. As we all know, the direction of magnetic field due to wire is found by right hand thumb rule, in which we have to place the direction of thumb in the direction of current and curl the finger. Curling of finger can give the direction of magnetic field. So see, thumb is in this direction because current is in this direction. Curling of finger, so finger comes outside. So due to this wire at point O, magnetic field is away. So I'll write due to this wire, magnetic field due to wire PC, it is mu naught I, that is current, it is 5 divided by 4 pi into a. The distance becomes equals to 5 centimeter. So 5 into 10 raised power minus 2 meter. So I'll write here 5 into 10 raised power minus 2, and direction is away. Similarly, my dear students, second wire is also of semi-infinite length. Let's discuss about the direction. So direction of current is like this, and curling of finger, so finger comes outside. So my dear student, due to wire PC and due to wire QD, due to both the wires, the direction of magnetic field at point O is same. So I am writing here magnetic field due to QD, it is nothing but mu naught into 5 upon 4 pi into 5 into 10 raised power minus 2, and it's due to this wire, the direction at point O, magnetic field at point O is away from the plane. So net magnetic field must be addition of both the magnetic field, that is QD. So B net becomes equals to mu naught into 5 upon 4 pi into 5 into 10 raised power minus 2 plus mu naught into 5 upon 4 pi into 5 into 10 raised power minus 2. So B net becomes equals to 2 into mu naught into 5 upon 4 pi into 5 into 10 raised power minus 2. 5 get cancelled, 2 2s are 4. So B net becomes equals to, instead of mu naught we can write 4 pi into 10 raised power minus 7. So B net is equals to, instead of mu naught we can write 4 pi into 10 raised power minus 7 divided by 2 is there, pi is there, multiply 10 raised by 2 is there. So pi get cancelled, 2 2s are 4. So B net becomes equals to 2 into 10 raised by minus 7 plus 2. So B net becomes equals to 2 into 10 raised by minus 5, and SI unit of magnetic field is Tesla. So net magnetic field at point O is 2 into 10 raised by minus 5 Tesla. I hope you all understand this concept as well. So let's move forward. We'll discuss other numerical. So please write down, my dear student. Next numerical, two identical coils P and Q. Two identical coils P and Q. Please write down next numerical. Two identical coils P and Q. So next numerical we'll discuss is identical means radius and other things are given. So write down two identical coils P and Q, each of radius capital R. Each of radius capital R are lying in perpendicular planes. 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 Are lying in perpendicular planes, such that they have common center. 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 Full stop. Find the magnitude and direction. Find the magnitude and direction of the magnetic field. Find the magnitude and direction of the magnetic field at the common center of the coil if they carry current equal to I and root 3I. If they carry current equal to I and root 3I respectively. So see, my dear student, the question is, we have two coils, one is P, another is Q. In both the coils current is flowing. The coils are placed in such a way that both the coils are perpendicular to each other. Their center is common. So this is basically Q coil and this is basically I coil. Both the coil carry same current. One is not same current. Q coil carry root 3I current and P coil carry I current. I hope you all are understand now. See, for both the coils we want to find magnetic field at point O. So remember the formula: magnetic field at the center of the coil. Magnetic field at the center of the coil. Magnetic field at the center of the coil, it must be equal to mu naught I by 2R. I hope you all are aware. We'll derive this formula: mu naught I by 2R, where R is radius, I is current, mu naught is constant. So see, the direction of magnetic field due to current carrying circular arc can be found by right hand screw rule, in which we have to curl our right hand finger in the direction of current. Thumb can give the direction of magnetic field. I hope you all are aware this formula. So just try to understand, my dear student, how to find the direction of magnetic field. First of all, see, this is basically if I am talking about Q coil, then current will be like this, and for Q coil the current will be like this. So just try to understand the direction of magnetic field at point O, which is basically common center for both the coil. Try to understand, my dear student. So see, this coil will be like this, the coil is like this. So if coil is like this, so Q coil is in Q coil the current is flowing like this. So if current is flowing like this, I have to curl our finger in the direction of current. Thumb can give direction of magnetic field. So if I am curling the finger in the direction of current, thumb goes like this. So this is the direction of magnetic field at O due to current carrying Q wire. Similarly, if I am talking about magnetic field due to P wire, magnetic field due to P wire. So see, my dear student, this coil, the P coil is like this and current is flowing like this. So if I am finding the direction of magnetic field due to P coil at point A, then it must be in upward direction. So this is the direction of magnetic field due to coil P, and this is the direction of magnetic field due to coil Q. Now see, my dear student, the magnitude must be magnetic field due to P coil is equals to mu naught I by 2R. Similarly, magnetic field due to Q coil mu naught root 3 I by 2R. This is the value of magnetic field at point O due to P coil, and root 3 I this is the value of magnetic field due to Q coil at point O. Now see, as you will see, my dear student, magnetic field is a vector quantity, and if any vector quantity at common point, there is not any possibility in two different directions. So here at point O, due to Q the direction of magnetic field is like this, and due to P the direction of magnetic field is like this. So from point O in two different directions magnetic field is executing, which is not possible. Under this situation we have to find net magnetic field. So net magnetic field must be, the formula is under root x square plus y square, means magnetic field along x-axis plus magnetic field along y-axis. So we can write along x-axis magnetic field is nothing but bq square plus bp and its square. So b net becomes equals to under root bq means mu naught root 3I by 2r and its square plus mu naught I upon 2r and its square. So just try to solve, my dear student. So what we'll get, just check it out. Remove the root and put the power to be half. So what we'll get b net becomes equals to mu naught root 3I upon 2r and its square plus mu naught I upon 2r its square and whole to the power half, because I'll remove the power. So just try to solve this root 3, and after solving this you will get the value mu naught I by r. So b net becomes equals to mu naught I by r. Now see, this is the direction of magnetic field due to Q coil, this is the direction of magnetic field due to P coil. So remember, if from common point, if two different directions in two different directions magnetic field is executing, then we have to find net magnetic field, and net magnetic field is always between both the, and if I want to find its direction, so let's suppose this angle is theta. So finding direction means to find tan theta, and we know that its formula is Pandit Badri Prasad har har bhole sona chandi tole. So tan theta is nothing but perpendicular upon base. So just try to find the value of tan theta, which gives you the direction. So tan theta is 1 by root 3. So 1 by root 3 means theta is equals to, tan theta must be equals to 1 by root 3. So it is equals to 30 degree. So theta is 30 degree. So the direction of net magnetic field is theta barabar 30 degree. I hope you all understand this concept as well. Now let's move forward. Let's discuss some more topics, my dear student. So please write down. Next topic is Ampere circuital law. Ampere circuital law and its application. Write down next heading, Ampere circuital law. Ampere's circuital law and its application. Write down next heading, Ampere's circuital law and its application. First of all, we'll discuss what actually Ampere circuital law is. So write down Ampere circuital law. First topic. Next topic is Ampere's circuital law. First of all, we'll discuss what actually Ampere circuital law is. So my dear student, with the help of Ampere circuital law, you will get the value of magnetic field. Similarly, like with the help of Biot-Savart's law, we'll get the value of magnetic field, but there is a limitation related to Biot-Savart law that we cannot find the value of net magnetic field due to hole conductor with the help of Biot-Savart's law. But with the help of Ampere circuital law, we can find the value of magnetic field due to hole conductor. Even the conductor carry infinite length. So write down first point, with the help of Ampere circuital law, with the help of Ampere's circuital law, with the help of Ampere circuital law, we can find the value of magnetic field. We can find the value of magnetic field due to hole conductor, even the length of conductor, is infinity. Even the length of conductor is infinity. So remember, with the help of Ampere circuital law, we can find the value of magnetic field due to even the conductor is of infinite length. Now see, just try to understand the formula, my dear student. So the formula of Ampere circuital law is closed integral B vector dot dl vector is equals to mu naught I. Just write it down. The formula of Ampere circuital law is closed integral B vector dot dl vector is equals to mu naught I. Closed integral B vector dot dl vector is equals to mu naught I. B vector dot dl vector is equals to mu naught I. If we'll open this, we'll get the formula B dl cos theta is equals to mu naught I, where write down, where, see my dear student, this formula is basically very much similar with Gauss's law, which we already studied in chapter first. In Gauss's law, the formula was E dA cos theta is equals to epsilon naught I. I hope you all are aware with the formula. So where theta is angle between magnetic field, where theta is angle between magnetic field and small length in Gaussian surface, where theta is angle between magnetic field and small length in Gaussian surface. See my dear student, like Gauss's law, Ampere circuital law is also defined with the help of Gaussian surface. So please write down the point where we want to find magnetic field. the point where we want to find magnetic field. The point where we want to find magnetic field is enclosed by the Gaussian surface. Is enclosed by the Gaussian surface. Remember, the point where we want to find magnetic field, we have to enclose that point with the help of Gaussian surface, and we all aware with the Gaussian surface. It is an imaginary surface which is enclosed the conductor in such a way that all the magnetic field lines which comes out from the current carrying conductor can passes over it. And remember, my dear student, this Gaussian surface is very much related to first chapter. So please go ahead with first chapter notes, revise it, then go through the lecture, then only you will capable to understand. So try to understand next concept. Remember, Ampere's circuital law is similar to Biot-Savart's law. With the help of Biot-Savart's law, we are finding magnetic field. Similarly, with the help of Ampere's circuital law as well, my dear student, we are finding magnetic field. But actually, Biot-Savart law carry a limitation. That limitation is, with the help of Biot-Savart law, we cannot capable to find magnetic field due to whole conductor together. But with the help of Ampere's circuital law, we can find the value of magnetic field due to whole conductor together. So please write down the definition of Biot-Savart's law. Ampere's circuital law. So Ampere's circuital law states that, write down, this law states that the line integral, this law states that the line integral of the magnetic field B vector, the line integral of the magnetic field B vector 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 around any closed current carrying conductor, around any closed current carrying conductor is equal to mu naught times the total current I, is equals to mu naught times the total current I passing through this closed circuit, passing through the closed circuit. So the formula of Ampere's circuital law is B vector dot dl vector is equals to mu naught I. And one more thing you have to remember, my dear student, this B vector dot dl vector can be write as B dl cos theta. And remember, here theta is angle between magnetic field and small length of the conductor. And remember, this small length is considered to be on Gaussian surface. Remember this thing, this small length dl is considered to be in Gaussian surface, and I already discussed in first chapter, theta, that is angle between magnetic field and small length, is always 0 degrees. So remember this thing, and magnetic field is always constant. So if magnetic field is always constant, then it comes from integration dl cos theta. So theta is basically always equals to 0 degree, and dl is basically length, a small length in Gaussian surface. If we'll integrate it, it will be converted into L, and remember, L is nothing but total length of the Gaussian surface, and this I is basically current inside the Gaussian surface. So please write down, dl is small length, consider in Gaussian surface, dl is small length, consider in Gaussian surface. Consider in Gaussian surface, first thing. Second thing, I is current inside the Gaussian surface. Current inside the Gaussian surface. Current inside the Gaussian surface. So remember, and one more thing that you have to remember, magnetic field is always constant. Magnetic field is always remains constant. Magnetic field is always remains constant. So if magnetic field always remains constant, then it comes from integration. Theta must be 0, cos 0 is 1, integration of dl. So integration of dl is L, and remember L is nothing but total length of the Gaussian surface. So this is what actually Ampere circuital law is. Please my dear student, remember the formula. The formula of Ampere circuital law is closed integral B vector dot dl vector is equals to mu naught I, and with the help of this formula we will find the value of magnetic field due to even infinite long current carrying conductor. So let's start applying this formula. First application my dear student of Ampere circuital law is, please write down, first application, magnetic field due to, write down, magnetic field due to current carrying, magnetic field due to current carrying thick, magnetic field due to current carrying thick infinite long wire, magnetic field due to current carrying thick infinite long wire, infinite long wire of radius A, of radius A at point P, of radius A at point P, x distance apart, x distance apart from the center, x distance apart from the center of the current carrying wire, from the center of the current carrying wire, from the center of the current carrying wire. So I am repeating once again, magnetic field due to, magnetic field due to current carrying infinite long thick wire, infinite long thick wire of radius A at point P, x distance apart, x distance apart from the center of wire, from the center of wire. So topic is magnetic field due to current carrying infinite long thick wire of radius A at a point P, x distance apart from the center of the wire. So see my dear student, what actually thick wire is. So thick wire is basically that type of wire through which current is flowing from everywhere, Remember, thick wire means the wire from where the current is flowing everywhere, because thick wire means the wire is, inside and outside, both from both the part the current is flowing. So this is our thick wire whose radius is A, and this wire carry current I, and the wire is of infinite length. So this wire is of infinite length. We want to find magnetic field at any point P which is x distance apart from the center of the wire. So my dear student, this is our wire of infinite long length having radius A in which I current is flowing. So basically this view is side view. If I'll see from front, then you'll see my dear student, the current comes out from your side. So if current comes out from your side, here I am presenting dot for the direction of current. I am making the front view. So front view will be look like this. This is a infinite long thick wire in which I current is flowing. So if this is a thick wire, it means current comes from every point of the wire, because thick wire carry surface, and if surface is there, then current is capable to flow. So like this, my dear student, if I'll see from front side, front view, this is basically nothing but front view of the wire. This is side view of the wire. If I'll place like this, then current is coming from outside, coming towards outside. So basically this dot is nothing but direction of current. I am repeating this as, representing this as direction of current. So my dear student, let's suppose I current is flowing from this wire and radius of this wire is A. We want to find magnetic field at point P, which is x distance apart from the wire. Now see, this is point P where we want to find magnetic field, which is x distance apart from the center of this wire. So dear student, there are three possibilities which can take place here. First possibility is P point lies inside the wire. Second possibility is also there, P point lies outside the wire. And third possibility is also there, P point lies on the surface of wire. So please write down, there are three possibilities which can take place in this situation. First possibility, P lies outside. P lies outside means x is greater than A. See, A is radius of the wire and x is distance from the center to point P where we want to find magnetic field. So if P lies outside the wire, it means the value of x is greater than A. Similarly, second possibility is also there, P lies inside the wire. So I'll write here inside. So if P lies inside, it means A is greater than x. A is greater than x, or we can say x is less than A, then only P lies inside. And third possibility is also there, P lies on the surface. P lies on the surface. So if P lies on the surface, then we can say A must be equal to x. So there are these three possibilities are there for this given situation, that is I'm sorry, P lies outside, x is greater than A, P lies inside, x is less than A, and P lies on the surface, that is A is equals to x, or we can say x is equals to A. Now we'll discuss first case, that is if P lies inside. So please write down first case, P lies, first case let's discuss P lies outside. So write down case first. If P lies outside, write down case first, if P lies outside. So dear student, if P lies outside, then see how I'll find the value of magnetic field with the help of Biot's-Savart's law. So first case is if P lies outside, case first, if P lies outside. So if P lies outside, it means x is greater than A. So this is the wire, radius of wire is A, and current is comes out from the wire like this. This is O. From x distance at point P, we want to find magnetic field now. So this is basically the value of current. Total current flowing in the wire is I. Now see, if P lies outside and we want to find magnetic field at point P, first of all, we have to enclose the point P with Gaussian surface. And remember, the Gaussian surface must be spherical in shape. So this is basically the spherical Gaussian surface. Spherical Gaussian surface. Spherical Gaussian surface. So this is point, at point P, we want to find magnetic field. So for finding the value of magnetic field, we have to first enclose point P with spherical Gaussian surface. And the radius of this spherical Gaussian surface is x. Remember this thing. Now let's move forward. So see my dear student, the total current which is flowing in wire, I'll write here, total current flowing in wire is equals to I, and the wire is thick. Must remember, there is two kinds of wire. One is hollow wire and second is thick wire. Hollow wire means only outer surface is there, but if I am talking about thick wire, then from every point of the wire current is capable to flow, because a current acquire surface. So moving forward, come to the point, that is total current through the wire is I. So the formula is close integral B vector dot dl vector is equals to mu naught I. We can write it as B dl cos theta is equals to mu naught I. B comes outside because magnetic field, see, from point O, everywhere, if point P is present here, then also distance is x. If P lies here, then also distance is x. If P lies here, then also distance is x. So if P lies any point on this spherical Gaussian surface, distance remains same. So we can say magnetic field is constant. It comes outside. dl cos theta is equals to mu naught I. Now see, my dear student, as I already tell you, the angle between magnetic field and small length in Gaussian surface is always in same direction. So theta is also 0, mu naught I, cos 0 is 1. So B close integral dl is equals to mu naught I. Integration of dl is nothing but L. So L and mu naught I. L is total length of Gaussian surface. I'll write here, L is nothing but total length of Gaussian surface. Total length of Gaussian surface. So a Gaussian surface is spherical and sphere length is equals to circumference. It is 2 pi r. So L becomes equals to 2 pi r. R radius is x. So we can write 2 pi x. So B into 2 pi x must be equal to mu naught I. So B becomes equals to mu naught I upon 2 pi x. This is the value of magnetic field due to current carrying thick wire if point P lies outside the wire. Moving forward, write down case 2, if point P lies on the surface. So my dear student, if P lies on the surface, then the value of x becomes equals to A. So just replace x with A. So write down case 2, if point P lies on the surface of wire. Case 2 is if point P lies on the surface of wire. Case 2, write down case 2, if point P lies on the surface of wire. I am writing here case 2, if P lies on the surface of wire. So P lies on the surface of wire. So if P lies on the surface of wire, then x becomes equals to A. Now see, the value of magnetic field is mu naught I upon 2 pi x. Instead of x, I'll write A because P lies on the surface. I'll made it. This is the wire whose radius is A and current is coming towards us. That's why I am presenting the direction of current by dot, because current comes outside. This is point O. At x distance, P lies on surface of this wire enclosed with Gaussian surface. The value of radius and distance of point P where we want to find magnetic field is same. So instead of x, I'll write A. Now let's move forward. Let's discuss third case, if point P lies inside the wire. So please write down, if case 3, if point P lies inside the thick wire or simply wire. If point P lies inside the wire. We are discussing now case third, if point P lies inside the wire. Write down case 3, it is if point P lies inside the wire. So here comes case 3, if P lies inside the wire, that is x is less than A, my dear student. So let's see, this is our wire whose radius is A and the total current which is flowing through the wire is I. And remember, if wire is thick, then current is flowing from everywhere of the wire. Now what I'll say point P lies inside the wire. So if point P lies inside the wire, it means, just see my dear student, I'm making with different color. So this is the point P, which is x distance apart from the wire, a center of the wire, and this point P lies inside the wire. So if P lies inside the wire, just make the Gaussian surface. See, this is our spherical Gaussian surface. This is Gaussian surface. Gaussian surface. As we all know, the point where we want to find magnetic field, first of all we have to enclose the surface. See, so my dear student, total current in this wire is I. I'm writing here total current in wire is equals to I. The formula is closed integral B vector dot dl vector is equals to mu naught I. We can write this as B dl cos theta is equals to mu naught I. B comes outside because magnetic field is constant, and angle between magnetic field and small length which is taken on Gaussian surface is always 0. So cos 0 is equals to mu naught I. So B close integral dl, because cos 0 is 1, mu naught I. So B into, instead of dl we can write L, mu naught I. So here my dear student, L is length of the Gaussian surface and this I is current in Gaussian surface. I am repeating once again, this L is length of Gaussian surface, length of Gaussian surface, and this I is nothing but current in Gaussian surface. Current in Gaussian surface. So see my dear student, here the total current is flowing in a radius wire, but the Gaussian surface is less than a radius wire. So inside the Gaussian surface, the value of current is not I. It must be something else. So let the current, I am writing here, let the current in Gaussian surface, let the current in Gaussian surface is equals to I dash. So if current in Gaussian surface is considered to be I dash, then our formula is also be I dash, because this I is nothing but current in Gaussian surface. I am repeating once again, this I current is flowing in total surface of the wire, and the Gaussian surface is less than the total surface of wire. If you will compare, you can see. So first of all, we have to find the value of current which is flowing in Gaussian surface, that is I dash. So see my dear student, this is thick wire, and for this wire the current is flowing through its area. So total area of loop, if I am asking total area of loop is nothing but pi a square. So in area pi a square, the current is I. So in unit area means 1 meter square, the flow of current must be I by pi a square. I hope you all are understanding. So in unit area, the current is I by pi a square. Now see, we want to find the current in Gaussian surface. So what is the area of Gaussian surface? I am writing here, area of Gaussian surface. Area of Gaussian surface must be pi x square. So if in unit area, that is 1 meter square, if the flow of current is I by pi a square, then the value of current which is flowing in this given area must be, so current in pi x square, current in pi x square must be I by pi a square into pi x square. Pi and pi get cancelled. So the current, that is I dash, which is current in Gaussian surface, is nothing but I x square by a square. I hope you all are understanding. Now we'll put this value. So I x square by a square. Now put the value in formula. So we'll get B into L. L is length of Gaussian surface, which is equals to circumference of the Gaussian surface, and the radius of Gaussian surface, my dear student, is x. So 2 pi x. So B into 2 pi x is equals to mu naught I dash. So we can write B into 2 pi x is equals to mu naught. Instead of I dash, which is current in Gaussian surface, we can write I x square by a square. So B becomes equals to, see, x and x get cancelled. So we'll write here mu naught I x upon 2 pi a square. This is the value of magnetic field due to current carrying thick wire if point P lies inside the wire. If point P lies inside the wire. I hope you all understand this concept as well, my dear student. Let's move forward. Write down next application. Magnetic field due to current carrying. Write down next application. Magnetic field due to current carrying hollow cylindrical wire. Magnetic field due to current carrying hollow cylindrical infinite long wire. Magnetic field due to current carrying hollow cylindrical infinite long wire. Hollow cylindrical infinite long wire. Hollow cylindrical infinite long wire. So see, my dear student, what I'm asking is, the topic is magnetic field due to current carrying infinite long hollow cylindrical wire of radius a at a distance x from the center of the wire. So magnetic field due to current carrying infinite long hollow cylindrical wire of radius a at a distance x from the center of the wire. Now see, my dear student, what actually hollow wire is. Hollow wire means from inside the wire no surface is there. So this is basically side view of hollow wire. This is of infinite long length, and the radius of hollow wire we are considering is a. Now see, this is hollow wire. So if this wire is hollow wire, then current only flows on its surface. Remember, in case of hollow wire, the current only flow on its surface, because to flow of current we need surface, we need any surface, any ground. So if I am talking about hollow wire, then hollow wire from inside it is empty, so only surface is there. So if only surface is there, then current is only capable to flow from its surface. So see, my dear student, we have a hollow wire whose radius is a. In the hollow wire, the current is flowing is I, and we want to find magnetic field at any point P, which is x distance apart from the center of the wire. Now see, if I'll say its front view, so this is basically nothing but front view of this hollow wire whose radius is a. Inside the hollow wire nothing is there, no surface is there, so current only flow from its surface. That's, I'll mark the direction of current is away from the plane, that's why I made it as dot. So this is the direction of current, and the total current which is flowing from this hollow wire is I. So my dear student, three cases are possible. Cases are possible are, first, P lies outside. So if P lies outside, it means x is greater than a. Second possibility is P lies inside. So if P lies inside, then x is less than a. Third possibility is also there, P lies on the surface. So if on the surface I am talking about, then x must be equal to a. So three possibilities are there, P lies outside, P lies inside, and P lies on the surface. First x is greater than A, second x is less than A, and third x is equals to A. So moving forward, let's discuss case first, that is if P lies outside. So write down case 1, if P lies outside. Case first, if P lies outside. If P lies outside. If P lies outside. Case first is if P lies outside. So write down case first, if P lies outside. So if P lies outside, it means x is greater than A. So this is how we'll solve it. This is the wire, hollow spherical wire whose radius is A, and this is, as wire is hollow sphere, so current only flowing from its surface. So this is the direction of flow of current. This is center. From x distance we have a point P where we want to find magnetic field. So just we know that the formula is closed integral B vector dot dl vector is equals to mu naught I. This formula can also write as B dl cos theta is equals to mu naught I, where theta is nothing but angle between magnetic field and small length. So theta must be 0, magnetic field is constant. So dl cos 0 is equals to mu naught I. So integration of dl is nothing but L, which is equals to mu naught I, and we all know about the associations, that is L is nothing but length of the Gaussian surface. So see, this is point P, enclose this point P with Gaussian surface. The Gaussian surface must be spherical in shape, simple. So this is our Gaussian surface. So my dear student, the length of Gaussian surface is equals to its circumference. So it is equals to 2 pi x. So I'll write here 2 pi x, which is equals to mu naught I. So B becomes equals to mu naught I upon 2 pi x. This is the value of magnetic field due to current carrying hollow cylindrical wire if P lies outside. Now let's discuss case second, if P lies inside. So please write down if P lies inside the wire. Write down case 2, if P lies inside the wire. If P lies inside the wire. We are discussing now case 2, if P lies inside the wire. So please write down if P lies inside the wire. Case 2, if P lies inside the wire. So see my dear student, this is wire in which this is hollow spherical wire. So if wire is hollow spherical, then current always flow from its surface, and the radius of wire is A, and P lies inside means x is less than A. So this is O. At x distance apart, we have a point P where we want to find magnetic field. We all know the formula. The formula is closed integral B vector dot dl vector is equals to mu naught I. This can also be write as B dl cos theta is equals to mu naught I. Theta must be 0. So we can write P dl cos 0, which is equals to mu naught I. Now see, B is constant, integration of dl is equals to mu naught I. So integration of dl is L, which is equals to mu naught I. Now see my dear student, this I is current in Gaussian surface. So first of all, we have to make a Gaussian surface by taking reference of point P where we want to find magnetic field. So see dear student, this value of current must be 0 because inside the wire no current is there. So it means I is current inside the Gaussian surface. So value of I is 0, hence the value of magnetic field inside the hollow spherical wire is also equals to 0. Now let's discuss case 3. If point P lies, case 3, if point P lies on the surface of wire. So if P lies on the surface of wire, my dear student, then X must be equal to A. So I am discussing case 3. If P lies on the surface, if P lies on the surface of wire. So if P lies on the surface of wire, it means X is equals to A. Now see, the value of magnetic field is mu naught I upon 2 pi A. I hope you all are understanding this concept. Mu naught I upon 2 pi A. So A must be equals to X. So we can write B equals to mu naught I upon 2 pi X. This is the value of magnetic field due to current carrying hollow spherical wire whose radius is A at inside the wire. So I hope, my dear student, you all understand two very easy applications of Biot-Savart's law. Practice more and more numerical. In next section, we'll discuss some more application of Ampere circuital law. Then we'll perform some numerical. After that, we'll move forward with some new topics called Lorentz force and Ampere's force. So thank you so much, my dear student. In next class, we'll discuss more topics. Till then, please take care, study hard, stay safe.